In section 5.1, we will explore exponential functions. The function f of x is equal to a to the x power, where x is a real number and a is greater than 0, meaning that it is positive, and a is not equal to 1, is called the exponential function with base a. The base needs to be positive in order to avoid the complex numbers that would occur by taking even roots of negative numbers. We are going to look at some exponential functions in just a moment, but first let's review some of the basic rules of dealing with exponents in general. In the following examples, we're going to rewrite the given expressions in the form 4 to the u power, where u is a constant or an algebraic expression. So we will write these as powers with base 4. Some other instructions may ask you to evaluate the expression, in which case you would actually try to represent the expression as a real number. But for these examples, we're simply rewriting these in terms of a base 4. First, we have the 9th root of 4. From previous rules, we know that we will write this as 4 to the 1/9 power. In general, the nth root of a number a is equal to a to the 1 over n power. So that is the rule that we're applying here. Secondly, we have 1 over 4 to the 5th power, and we will write this as 4 to the negative 5 power. And the rule that we're using here is that a to the negative n power is equal to 1 over a to the n. Next, we have 1 over the power 4 to the 3x. Same rule, we'll write this as 4 to the negative 3x power. Next, we have the 9th root of 4, all raised to the x power. Here, we're going to write this as 4 to the power x over 9. And the rule here is that the nth power of a, all raised to the mth power, is equal to a to the m over n power. Next, we have 1/4 raised to the x minus 8 power. First, we're going to write 1/4 as 4 to the negative 1. Keep the same exponent for now. And then, using the power of the power rule, we will write this as 4 to the negative x plus 8. So that rule that we just used is that a to the mth power, all raised to the nth power, is equal to a to the m times n power. So we multiply exponents. In this case, negative 1 multiplied by x minus 8 becomes negative x plus 8 for the new exponent. Next, we have 16 divided by the 3rd root of 4, or the cubic root of 4. We're going to do this in a couple of steps. First, we're going to write 16 as 4 squared. And then we're going to write the cubic root of 4 as 4 to the 1/3 power. Next, we're going to use the quotient rule of exponents to write this as a single power where we subtract those exponents. The rule that we're using here is that a to the m power divided by a to the nth power is equal to a to the m minus n power. 2 minus 1/3 we can rewrite as 6/3 minus 1/3. So as our final answer, we get 4 to the 5/3 power. So it's really important that if you don't feel comfortable with these rules of exponents, that you go back and spend some time reviewing them, because we will be using them quite a bit in this module. Now let's explore exponential functions and their graphs. For an exponential function, f of x is equal to a to the x power. We will have the following properties. When A, the base, is greater than 1, the graph will increase from left to right. It'll increase throughout its entire domain. The greater the value of A, the steeper the curve, the more rapidly the y-coordinates are going to grow. In the second case, when A is a number between 0 and 1, so think of it as a decimal between 0 and 1 or as a proper fraction between 0 and 1, the graph will decrease from left to right. In fact, it'll decrease throughout the entire domain. The smaller the value of A, the more steep the curve will be. In other words, it will decrease more rapidly. All of the graphs, regardless of the value of A being between 0 or 1 or being greater than 1, will have the same y-intercept at 0, 1. And this is because any number A to the 0 power is 1 as long as A is not 0, which it can't be because one of the rules is that A must be positive. All of the graphs will have the x-axis as a horizontal asymptote. Recall that the x-axis is the line y equals 0. The domain for all of these exponential functions will be the set of all real numbers. So let's just write that as an interval. And the range is the set of all positive real numbers. So for the range, we'll go from 0 to infinity with 0 not included. All exponential functions are one-to-one, meaning that they pass the vertical line test to be considered a function, but they also pass the horizontal line test to be considered one-to-one. This is important because that means that exponential functions do have inverses, which we'll discuss later in this module. Some additional characteristics for the graph of these exponential functions. We already mentioned that the point 0, 1 will be a y-intercept every time. We will have another point at 1, a for all graphs. Now this is not an intercept, but it's an important guiding point. We'll also have the point -1, 1 over a. These two additional points are easily obtained by just substituting 1 for x and -1 for x. If a is greater than 1, as we said earlier, we will have an increasing function. And if a is between 0 and 1, then we will have a decreasing function. Characteristics 3 and 4 have already been discussed above. Now here are some generic examples of exponential functions. The one on the left has a base greater than 1. Therefore, we see that the graph increases from left to right. The second graph has a base that is between 0 and 1, and therefore we see that the graph is decreasing. You see that in either case, the point 0, 1 is a y-intercept. And then you have two additional guiding points that are easy to obtain, 1, a and -1, 1 over a in each graph. Now we're going to be talking about other graphs in this module, and an easy way for you to remember what exponential graphs look like, I refer to them as J-shaped graphs, kind of like because they look like the letter J. Now, the letter J doesn't exactly capture the shape because, of course, we don't go back up here in the tail, and we also don't have the little hat here. But in general, it reminds me of the letter J. In the second case, it's kind of like the J got reversed, and so I'll call it a T-shaped graph, or whatever you want to call it. Anything that will help you remember the overall shape. You don't have to refer to these as J-shaped graphs. That's just my preference to remember them. Whatever works for you, go ahead and use that as a way to remember the overall shape. Now, these are parent graphs. So In these two cases, we have the function f of x is equal to a to the x power. So we consider these both parent functions, but we can apply transformations if there is any modification to x or to the entire function. So let's discuss briefly how to deal with transformations. If there is a real number subtracted from x in the exponent, that is going to create a horizontal translation, h units either to the left or the right, depending on whether h is positive or negative. And then if we add k at the end, that is going to create a vertical translation, k units up or down, depending on whether k is positive or negative. Additionally, we can have reflections created. Remember that if we multiply the input x by -1, that is going to create a horizontal reflection. And so that is going to go over the y-axis. Just adding this here because it wasn't pre-printed in the notes. And if we multiply the entire power by a -1, then that is going to create a vertical reflection. And so that is over the x-axis. An important note, and this is something that we saw in our previous module, is that any reflections need to occur before vertical translations. Let me say that again. Reflections occur before vertical translations. So if you have multiple transformations, you're going to take care of any horizontal translations first. Reflections next, and vertical translations last. If you have any stretching or compressing, that could happen at any time, either at the front end or at the back end or sometime in the middle. It doesn't matter when you do the stretching and compressing, but for translations, you want to do horizontal translations first, if there are any, then take care of all of your reflections, then do your vertical translations last. The order actually will matter. Just like there's an order of operations, there's an order of transformations. All right, let's take a look at the following two examples. First, we have the parent function f of x is equal to 2 to the x power. Here, a is equal to 2, so a is greater than 1, so we expect the graph to increase from left to right, and it will. Let's do a quick table of values so that we can figure out how to plot some guiding points. First, when x is 0, y is equal to 2 to the 0 power, which is 1. We expected that point because we discussed earlier that this will always be the y-intercept. When x is 1, y is equal to 2 to the first power, which is 2. We also expected this point because this is the point 1, a. Let's go to x equals 2. Then y is equal to 2 to the second power, which is 4. When x is 3, y is equal to 2 to the third power, which is 8. I think this is going to give us enough points to the right of the y-axis. So let's do 0, 1, 1, 2, 2, 4, and 3, 8. We get a sense of that shape here on the right. Now we're going to need some additional points to the left of the origin so that we can see how to complete the graph in that second quadrant. So let's see, when x is -1, y is equal to 2 to the -1 power, which is equivalent to 1/2. We expected this point. This is the point -1, 1 over a. So -1, 1/2, right there. When x is -2, y is equal to 2 to the -2 power, which is 1/4. And so we see that we get closer and closer to the x-axis. However, as we continue moving to the left, we will get smaller and smaller values of y, but they're never going to quite reach 0. So what's going to happen here in this second quadrant is that the curve is going to keep getting closer and closer to that x-axis, but the x-axis is going to be a horizontal asymptote. So I'm going to add that here as a green dashed line to show us that that is an invisible barrier. The domain here is the set of all real numbers, so there's no restriction on x. And you see here that the range goes from 0 to infinity with 0 not included. So in other words, the range includes all positive values. In the next example, we will have a transformation of this very same parent function. We have f of x is equal to negative 2 raised to the x minus 3 power and then plus 3. I see 3 transformations here, and it's very important to note that the base of that power is still a positive 2. We're just multiplying the entire power by a negative 1. Remember that the base must be positive. So I see 3 transformations. I see a horizontal translation, 3 units to the right. Then I see a vertical reflection. So we will reflect over the x-axis. Oh, let me write that a little bit more clearly. Over the x-axis. And lastly, I see a vertical translation 3 units up. And remember that the order in which you do the transformations will matter, so you want to make sure you do them in the proper order. We're going to move the graph that we just created 3 units to the right, then create a vertical reflection over the x-axis, and finally we're going to move the graph 3 units up. So we're going to have to do this in steps. First, if I move the graph 3 units to the right, that original 0, 1 y-intercept is going to move 1, 2, 3 units to the right. Then the rest of the graph moves with it. So after moving the graph 3 units to the right, we get something like this. Next, we have to do a vertical reflection over the x-axis. So I'm going to go ahead and reflect the points across the x-axis, and I have a couple of guiding points here, but in general, it'll look something like this. It's not exact, but it's pretty close. Then we are going to move everything up 3 units. So I'm going to do this one in blue. So this green point here that right now is at 3, negative 1, that's going to move up 1, 2, 3 units. This next point is going to move up 3 units. And we see that the horizontal asymptote, which right now is sitting still at the x-axis, that's going to move up 3 units as well. So I'm going to add that here to help make sure that as I complete the graph in blue, that I observe that horizontal asymptote. We're going to go somewhere like this. So the blue graph is our final graph. Remember, we got here in 3 steps. First of all, we took the graph that we created just a moment ago, moved it 3 units to the right. Then we reflected vertically across the x-axis. And finally, we moved up the graph 3 units. For the domain, I see that we still have all of the real number line. There's still no restriction on x. The range is different though. We see that there is a horizontal asymptote at y equals 3. So the range will go from negative infinity, because there's no lowest y value, up to but not including 3 for y.